This is a brief follow-up video to the video I did with the lock-in amplifier and an audio source driving a signal generator to an ultrasonic transmitter, which then received the signal and that was basically played on a speaker. This time I have an AWG data source, which for this particular experiment sends a simple pattern, it's a data pattern, into the modulation input of the signal generator, which then sends the same data stream to the transducer and received through a lock-in. And this time, since I cannot play it as sound, I'm going to display that as a signal on an oscilloscope. It's possible, of course, to take this data, capture it, and using some kind of a data recovery system like a clock and data recovery unit, we could actually recover the data that's sent by the AWG. Since the data can have very low frequency and high frequency information in it, it may require some intelligence on how to recover the data. That's a whole new separate topic on clock and data recovery. I won't go into that, but I just want to illustrate the point that the lock-in will actually recover the baseband or the signal that is contained in the ultrasonic signal, which is a much higher frequency. So data in this case is 2 kilobits per second. The clock is the ultrasonic signal is at 40 kilohertz, and so this data rate is much lower than what the carrier is containing, so it should work fine. What I have here is somewhat random data. So that data is now going into the modulation input of my HP3325A, which is producing a 141 kilohertz ultrasonic tone, which is then modulated by this lower frequency data. That goes into this transmitter of the ultrasonic driver over here, and that's placed about a meter or so away, and it's being received by this other receive sensor, the input of which goes, the output of which goes to the lock-in. And you can see the signal is fairly strong, usable data coming out of this lock-in, and as you can see over here, this is the recovered data coming out of the lock-in X magnitude output, and it's fully usable in terms of it basically compares well with what is going in to this ultrasonic sensor. And if this is decoded, it should produce the same data that is being transmitted up there. Now if I change the frequency even slightly, that is if the reference in the lock-in is not exactly at 41 kilohertz, you'll see what happens now. So now I'm using a 41 kilohertz internal reference, and you can see that the lock-in is basically amplitude is almost gone. It's basically not able to recover it correctly, and you'll see that the output also looks totally wrong. As you can see, it doesn't match what is going in. So one has to have the frequency exactly right in order to be able to recover data from a lock-in amplifier. Going back to the external reference, it now recovers the data. The signal amplitude is much better, 11 millivolts, and the data looks correct again on the scope.
So in this demo, a lock-in amplifier was used to recover a digital data pattern embedded in an ultrasonic sound signal, and this was transmitted from a transmitter, ultrasonic transducer, to an ultrasonic receiver a short distance away. The received signal from the IQ output of the LIA, the lock-in amplifier, was displayed on an oscilloscope this time, and the received signal matched the transmitted data in this simple example by visual inspection. The data rate was 2 kilobits per second, which is the maximum transition frequency in that data pattern I had put in there, and this was on top of a 41 kilohertz ultrasonic carrier. This is AM modulated again. The average DC in this pattern is 0, which of course makes it easier to detect. In general, bandwidth limitations and different types of encoding schemes will change the way the signal appears at the output of the lock-in and might dictate the need for an appropriately designed clock and data recovery system that uses this LIA output. Shorter time constants in the LIA will of course reduce the ISI, the intersymbol interference, since the signal bandwidth will be enhanced, and this will allow for the easier recovery of the digital data. So here was a fairly trivial example where the transmitter, receiver, the lock-in, and the data recovery all in the same location. So it's pretty easy to send the clock around to both the transmitter and the lock-in. But over longer distances, a means to provide the exact clock to the lock-in amplifier will need to be devised, since it's not obvious how to get the exact frequency to both these systems. And there are various ways to do this, but that's something to think about and way beyond the scope of this brief video. Thank you for watching. Hope this was informative. See you next time.